Okay, so let's have a go now with problem 3.1 from Wald's General Relativity, where he wants us to let property 5, which is the torsion-free condition, be dropped from the definition of the derivative operator as defined in section 3.1. And then in part A, we are to show that there exists a tensor T called the torsion tensor, such that for all smooth functions f, we have this relation between the covariant derivatives and the torsion tensor. And so the hint is to repeat the derivation of equation 3.1.8, letting nabla tilde be a torsion-free derivative operator. So just let's first of all write down a couple things here. So we're dropping the torsion-free condition, so it's no longer true that nabla A, nabla B of f is equal to nabla B, nabla A of f. But as per the problem statement, nabla tilde A still has this property. So let's just keep this in mind going forward. And with that, we can get started by just copying down 3.1.7, which I've written up here, or copy pasted up there rather. Nabla A, WB equals nabla tilde A WB minus C, where C is just some tensor field WC. Now, since we're going to follow the derivation of 3.1.8, we're going to do what they did in the text, which is let omega B be nabla B of f, which consequently is also nabla tilde B of f. So with this, we can rewrite the top line like this. Now remember, we're looking for an expression that has this on the left-hand side, the nabla A, nabla B of f minus nabla B, nabla A of f. So let's take this equation and subtract it from itself, where the subtracted version has the b's and a's flipped. So that's going to look like this. Nabla A, nabla B f minus nabla B, nabla A f. So we have the same thing with the tildes here. And then we're going to have something like okay, but we can recall from up top here that the nabla tildes are torsion free still, so these actually just end up canceling to 0. And so what this means is that we get minus nabla C of f, C C A B minus C C B A, or in other words, let's say 2 times the antisymmetric part of C. So it's just another way of writing the difference between these two terms. And then if we define this to be T, then we get, I'll write the entire thing here, nabla A, nabla B of f minus nabla B, nabla A of f equals minus nabla C of f times T C A B, where T is that torsion tensor. Which is exactly what we were asked to show. Okay, let's get started with part B now. So he's going to ask us to show that for any smooth vector fields xa and ya, we have this relation between the torsion tensor, the x's and y's, and the commutator of x and y. Okay, so to start this, we're just going to start by expanding the commutator acting on a scalar function f. So this is going to be x, y on f minus y, x on f But since y and x are smooth vector fields, we can write these as components times derivatives. So let's do this like this. We're going to have xa nabla a yb nabla b on f minus y b nabla b xa nabla a on f. Okay, so we can do some product rule type things here. So this is going to equal, we're going to pull out the xa and then get two terms out of the way this derivative x on these brackets. So we're going to get one term that looks like this, delta a y b del b. Sorry, I shouldn't be saying delta, it's nabla a. And then we're going to get another term with the, with the y out front, nabla a, nabla b. Remember, these are going to be acting on f. I should have an f here and an f here. And so those are the first two terms, and then we're going to have minus another product rule with this yb out front. So we're going to have one term like this, delta nabla b x, a nabla a f plus xa nabla b nabla a f. So we can kind of collect some terms and reorganize this a little bit now. So we're going to have a term like this. We're going to have xa nabla a yb nabla b f minus yb. So now I'm onto this term here. Nabla b xa nabla a f plus, and then we're going to collect the xa and yb. These are components, so it's okay if they move through each other. And we're going to have nabla a, nabla b on f minus nabla b, nabla a on f. So this, as per part A, is simply minus t cab times nabla c of f. So we can rewrite this all. And in rewriting it, I just want to make sure that I have my a's and b's where I want them. Okay. Oops. I'm going to switch my dummy variables here, and I'm going to write these b's as a's and these a's as b's. Plus, now here I'm going to rename b to c and c to b, I believe, in this term. So let me just write that up here. B to c, c to b. So we get xa, yc times minus t b a c nabla b f. Okay, so now what we're actually interested in is the component of the commutator, if you remember. So we what actually shows up in this equation is the component of the commutator x and y, and we just have the commutator of x and y acting on f. So let's actually like pull out the component now. For us, this is going to be the bth component. So x, y, bth component is xa nabla a yb, and then we're going to take away the nabla bf here. Not take away, but like it's not included. xb, and same thing here, the nabla bf goes away, and we get minus tbac xa yc. Now we can rewrite this in terms of having the torsion tensor and these x's and y's on the left-hand side, so let's do that. TBAC XA YC equals XA nabla A YB minus YA nabla A XB minus this commutator of x and y, the bth component, which is what we were asked to show. I think I may have my indices labeled slightly differently than the problem asks for, but it's the same thing. Okay, now we can do part C. So we're supposed to show that given a metric GAB, that there exists a unique derivative operator nabla A with torsion T such that nabla C GAB is 0. And then we are asked to derive the analog of equation 3.1.29 expressing this derivative operator in terms of an ordinary derivative and the torsion tensor. Okay, so we can start here by writing, so this is 3.1.29 that we want to derive an analog of eventually, but we can start here by writing 3.1.23, which comes from 3.1.14, and basically this just says nabla A on GBC is nabla tilde A on GBC minus C DAB G DC minus C GAC GBD is 0. So we can let these metrics act on these C's and lower the indices, so we can rewrite it like this. CAB lower minus CBAC. And eventually we're going to want this in terms of the normal derivative operator, like I said, so we can just also write this as del A GBC minus C CAB minus C BAC. Okay. Now we're going to consider the combination nabla A GBC minus nabla C GAB plus nabla B GCA. So this is going to give us nabla tilde A GBC minus C DAB GDC minus C DAC GBD minus nabla tilde C GAB minus C DCA GDB minus C DCB GAD and actually we're going to add this last term, not subtract it, right? So this is plus nabla tilde B GCA minus C D BC GDA minus C D BA GCD. So we can kind of write this together as a line now. So let's collect the nabla stuff first. So we get nabla tilde A GBC minus nabla tilde C GAB plus nabla tilde b GCA minus, okay, and then we're going to have C, it's this term, C CAB minus C BAC, then minus minus is plus C BCA. All I'm doing here is rewriting them with having let the metric act on the indices to lower them. Then we have another minus minus, so this is a plus. We get C ACB minus C ABC minus C CBA. Okay. But we know that this right here is just T BAC. This right here is just T ABC. And let's see. So we can rewrite this this way. Of course, this is all going to equal 0, right? So, and we also know that, just put us on the side here, minus C CAB minus C CBA equals minus 2 C CAB, like this. So we can pull that over to the 0 side here, and we get that, or not the 2, but just the C CAB equals, then the 2 is going to go this way, so 1/2, and then we get these. Now I shouldn't have even written these as nabla tildes because we're doing this in terms of the ordinary derivative, so let's make that change now. Nabla A GBC minus, not nabla, sorry, del C GAB plus del B GCA plus T BAC plus T ABC. Okay, but we can actually rewrite this CCAB thing. So we know, this is probably a roundabout way of doing this, but we know that CCAB is the sum of the symmetric and antisymmetric parts. But this just equals CCAB plus 1/2 T CAB. So that means that CCAB equals CCAB minus 1/2 T CAB. So we can make a substitution here and say something like CCAB on the left side equals 1/2 of all this stuff we already had. Del A GBC minus del C GAB plus del B GCA plus T BAC plus T ABC, and now we add our last little bit in here, so this is going to be plus T CAB, and there we have it. So this is our analog of equation 3.1.29, where we also have, where are they? These factors of the torsion tensor. So now that we have C in terms of these partial derivatives as well, I'll put a box around this. C in terms of partial derivatives in the torsion tensor, we can go back up to where we originally wrote this down. And we realize that now the covariant derivative here is uniquely determined because we have a specific value for these C's in terms of these del's and torsion tensor only. So that's the only thing it can possibly be.